Okay. All right, so before I get into that first paragraph about, ladies, what happens when I have a right triangle and draw the altitude to the hypotenuse, let's come back to that problem one that I told you and you know how to do. Triangle what is similar to triangle what is similar to triangle what. So hopefully you have something along the lines of, let's say, triangle EGA would be similar to triangle EAK, which will be similar to triangle AGK. Now, once again, remember, by all means, your answer could look different from mine and still be right, as long as whatever order change happened in this first triangle also happened in the second triangle and also happened in the third triangle. Okay? What this lesson is about, or the big chunk of what happens in this lesson, is the fact that when we have a diagram like this, where a right triangle has an altitude drawn to its hypotenuse, as you can see, we end up with three similar triangles. And because of those similar triangles, we end up with a couple of interesting proportions. Before we get into why those proportions are deemed interesting, there's a little bit of vocabulary we need to get to. I see some of you looking into your laps. Your lap is not that fascinating. I know it's your phone. Put it away. You're not fooling anyone. Okay, so let's backtrack. You see in our notes that we're talking today about geometric mean, and that may be something new to you. However, the term arithmetic mean is not. When you think about the word mean in math, besides old lady Clouse, what else comes to mind when you hear the word mean and you think math? Average, fantastic. And when you take the average of two things, think about what you're doing. You are adding those two things and then you are dividing by 2. The geometric mean is basically that taken to the next level. So let's think about it step by step. The first step of finding an arithmetic mean is adding two things together. If I'm taking addition to the next level, what is that? Multiplication. So when we are taking the geometric mean of two numbers, the quick and dirty version, as I like to say, is you start by multiplying the numbers together. And then, what? Let's backtrack back to arithmetic mean. After you add the two numbers, you then divide by 2. So think along the lines of, what is dividing by 2 taken to the next level? Ooh, very good, yes. So to find the geometric mean of two numbers, you multiply, then square root. However, in your notes, you see that they're expressing geometric mean in a completely different way. I want to make sure to talk about geometric mean in both contexts. In the context of just find the geometric mean of two numbers, and what does the geometric mean look like as far as this lesson goes. So in that paragraph, it says, occasionally in proportions, I'm looking at that second line, the means are equal to each other. So a little bit of vocabulary when we're talking about a proportion. When we're talking about a proportion, there are means and there are extremes. The means are these two numbers. So based on what was described to us in that sentence, the mean is the same, the means are the same number, so they're both x. And if I was taking the geometric mean of A and B, according to our lesson, this is how we find the geometric mean of two numbers. We set up a proportion like this. And think about what we would be doing if we were trying to solve for x here. We would cross multiply, so we'd be multiplying A and B together. See that multiply? And then I'd have x squared on the other side of the equal sign. But how would I then solve for x? by taking the square root. Okay, so just two different ways that I want you to think about finding the geometric mean. So in problem 2, like I said, it's just numbers. So we'll deal with the quick and dirty version. Multiply the numbers and then take the square root. So for problem 2, we're multiplying 5 times 12. We get 60. And then we're taking the square root of 60. And, oh, Mrs. Clouse, this is just way too easy. Certainly there's got to be a twist. Of course
I know the twist.
What's the twist?
You have to
We have to simplify the radical. You talked to Casey during lunch?
Yeah.
Okay, so let me refresh your memory on what Caitlin is talking about. I do not want you typing 60 and then hitting the square root button in your calculator. That is evaluating the square root. I don't want you to evaluate the square root. I want you to simplify the square root. Theoretically, you've seen this before. This is an algebra skill. It's come to my attention, however, that a lot of you are seeing this for the first time, and I apologize on behalf of your algebra teacher. I will try to kind of step-by-step it as much as I can through the process, but we do have to kind of go through it as if we're assuming that you've seen this before. All right, so what you're looking for is what perfect square factor does 60 have? It's divisible by 4. Before I go any further, when I say perfect square, are we all talking the same language, or do I need to clarify that a little bit? All right, you got that. Okay, so perfect squares are numbers like 4, 9, 16, 25. You see what all these numbers have in common? If I were to take the square root of them in my calculator, they're all a nice, pretty number. Okay, they're all perfect squares. So, as Caitlin observed, 60 is divisible by 4. Well, what do I have to multiply that 4 by in order to get the 60 again? 15. And then, of course, ladies and gentlemen, you know what the square root of 4 is. It's 2. So the answer I'm looking for is 2 radical 15. Okay, take a moment with it. When we have a right triangle where the altitude has been drawn to the hypotenuse, a couple of really magically wonderful things happen. I want to make sure, however, that in the context of this lesson that we are referring to the segments in these diagrams using the same words. All right, so here's my original right triangle. And in my original right triangle, this is a leg. And this is the other leg. And because I've taught this lesson for many, many years and keep hearing students referring to these variables using the wrong words, I want to make sure that we have a key for this diagram. L represents legs. Too frequently I hear students refer to that L as length. They're all lengths. They're all segments. They all have lengths. This segment down here, that's the original hypotenuse. And some of you may be thinking, well, what do you mean by original hypotenuse? Remember, ladies, I'm drawing an altitude to the hypotenuse. So hopefully you're realizing that in these smaller triangles, the legs of my large triangle are now hypotenuses. I don't want you thinking of them that way, however. Let's use these letters as our common language. Okay, so A stands for altitude. H is hypotenuse. Notice that when I drew that altitude to the hypotenuse got split into 2 segments. We call those the segments of the hypotenuse. Okay, so again, very frequently I hear students refer to these as sides. They're all sides. The S's are segments of the hypotenuse. subscripts, as you can guess, are very important. Notice that L1, leg 1, is touching S1. It's adjacent to it. That comes into play in one of the later proportions that I give you. Okay, so this first property coming out of this diagram tells us that the altitude is the geometric mean. Remember that proportion version of geometric mean that I gave you? We ended up with these two things being the same. So the altitude is the geometric mean of the segments of the hypotenuse. That means this is S1 and S2. This is something that you were expected to memorize, not on the reference sheet. In my years, the best I've come up with is some apples are sour. Do you see what? Okay. It's a mnemonic device. Very much like, please excuse my dear Aunt Sally. Okay? If you can come up with something that helps you remember SA equals A over S, S over A equals A over S, run with it. Fantastic. Let me know about it. This is the best I can come up with. Okay? The next formula that comes out of these triangles says that each leg is the geometric mean of, let me stop reading. Leg is the geometric mean. So that means leg goes in those two spots. And it says it's the geometric mean of the hypotenuse and then the segment of the hypotenuse that's adjacent to that leg. Remember how I was talking about how S1 is touching L1 and S2 is touching L2? That's what I mean by adjacent. Okay? Yes, sir?
If you put the legs where the X and H are,
If these were L's and this is where the S and the H are, you'd end up with the same answer in the end. It just wouldn't look like a geometric mean. Okay? So, my mnemonic device, again, best I can come up with, snarling linebackers like hitting. I had a student this morning come up with sweet lions like hugs. That's pretty cutesy. I don't do cutesy. But if that helps you remember, write it down. Go with it. I just like snarling lines. What you got? I think that's hope oriented. Whatever works for you, run with it. Okay? Let's get refocused though, please. We haven't even used a problem. Ladies, gentlemen, we haven't yet done a problem with this yet. Stay focused. Once again, in an attempt to make sure that we're all speaking the same language in here as we're getting used to using these proportions, realize that I'm going to call this one the leg proportion, and I'm going to call this one the altitude proportion.
So you automatically have three sides that fill in just to know if it's a leg or altitude.
Say that again?
You already have the left fraction filled in as long as you know it's altitude or leg. And then you have the top part of the right one.
Well, theoretically, ladies, theoretically, you'd be solving for one variable. Okay, so for the most part, you end up...
Or numbers. Totally forgot.
Okay. Okay. We good from here? All right, let's put it in action. It's the same concept. Most of you are having no difficulty finding that x is 6. If you have difficulty with it, the proportion is on the screen. You can compare my work to yours. Okay, hopefully you're ready to compare your work against mine for Y. It's not a triangle, but if you look at it sideways,
It's a kite.
yes, it's still a kite, but notice the right triangle within it.
Do you not care about the bottom half?
It's not that we don't care about it. Read the question. The question is asking us for the width of this kite. And realize also, this isn't just an abstract kite on a piece of paper. The problem says Maggie has a kite, and she's trying to find the dimensions of it. So let's pretend that we are Maggie, and we have already solved this problem, and we are going to a kite builder and asking him to build the kite for us. In the end, when we find the dimensions of our kite, do you think that it is feasible that we will go to our kite builder and tell him, I want the kite to be 7^5 centimeters wide? No. Okay, because this is a real-world situation, our life is made a little bit easier. We don't have to simplify the radical. We can, at the end, just evaluate it. Okay? Woo! All right, now contain yourself. All right, but we have to get there first. So, this time I'm being asked for the width of the kite. What I would hope that you'd realize is, as far as what do I need to figure out in this problem, this segment here is the key to unlocking the problem. And then I ask myself, what is that? Is it a segment of the hypotenuse, leg, altitude? What is that? It's an altitude, so will I use the leg proportion or the altitude proportion? The altitude proportion. And what's in the other two spots? The 11 and the 25. So we cross multiply, get x squared is 275. And once again, since this is a real world situation, we're not going to go mucking about with simplifying the radical. We're just going to punch that into our calculator and evaluate it, and I think we get 16.6.
If you round up.
Yes. Right, you can use the context. You know, in the context of this problem, a radical answer really doesn't make a whole lot of sense. Right. Okay? So, am I done with this problem? Have I answered the question? No. What do I need to do to find the width of the kite? Double it, yes. Okay, so the width equals 33.2 inches. This last problem is challenging, not so much in the geometry of it, but the algebra that shows up thereafter. So, since the x that we're trying to solve for is a segment of the hypotenuse, and I look at the 9 and I realize it's the other segment of the hypotenuse, I could put them together and get the whole hypotenuse, and then finally the 20 is a leg. So since nowhere in this proportion do I have to deal with the altitude, I would hope that you'd realize that what we're using is the leg proportion. That's this guy right here again. Okay, so the 20 goes in the two L spots. The segment of the hypotenuse that's touching it is x, and then the whole hypotenuse is x plus 9. Well, nothing's too complicated so far until I go to cross multiply, and I get that x squared plus 9x equals 400. And then this involves some algebra that we haven't dealt with yet this year in the regular classes. We've talked about it a little in the honors classes. So at this point, because I have a quadratic, meaning I have that x squared term, and since I also have that x term, what you want is everything on one side of the equation. So I'm going to subtract the 400 from both sides and get x squared plus 9x minus 400 equals 0. And what you need to realize comes next is the process of factoring this trinomial. So what we're doing, again, is kind of the opposite of FOIL. And since you know that this term has to come from my first terms in both parentheses, you know that x times x is what's going to give me that x squared. Since our last term is negative, I know the signs in my parentheses are opposites, meaning I've got one positive and one negative. And then finally, I've got to come up with the two numbers inside the parentheses. So the way that I teach this algebra is to look at that last number, that 400, and ask myself what factors of 400, what two numbers that multiply together to give me 400, what factors of 400 will multiply together to give me that 400, but when I subtract them, I get 9. And 400 is a kind of big number, so it's understandable if it takes you a little bit to realize that the two numbers are 25 and 16. If I multiply 25 times 16, I get 400. If I subtract 25 minus 16, I get 9. But you can't just throw those numbers haphazardly into those parentheses. You have to be mindful about which number goes where. When the signs in the parentheses are opposites, this sign, whatever it may be, will go to our larger factor. So since 25 is bigger than 16, I put 25 with the positive sign and 16 with the negative sign. And since now I have two things being multiplied together to get 0, I know one of them has to equal 0. That means I have two equations, and they are technical difficulties here, bear with me. My two equations are now x plus 25 equals 0, or x minus 16 equals 0. Now when I solve this equation, I get that x is negative 25. And when I solve this equation, I end up with x equals 16. But in the context of this problem, remember what x is. X is a segment. A segment cannot have negative length. So this value is no good to me. X is 16. And the question was asking me, how far does the robot travel from A to D? That is, in fact, the value of x. So we're done. It's 16 inches.